For centuries, humans have gazed up at the night sky and wondered, are we alone in the vastness of space? The sheer number of stars, like twinkling diamonds scattered across the cosmos, hints at the possibility of other worlds. But are any of these distant planets like our own Earth capable of supporting life as we know it? This question, fundamental to our understanding of our place in the universe, drives scientists to search for Earth-like planets beyond our solar system. The quest to find another Earth, a twin planet orbiting a distant star, is one of the most exciting scientific endeavors of our time. It's a search that pushes the boundaries of technology and our understanding of the universe. A journey fueled by curiosity and the hope of discovering that we are not alone. When astronomers talk about Earth-like planets, they are looking for specific characteristics that resemble our home planet. These characteristics are not just superficial similarities, but delve deep into the planet's composition, atmosphere, and potential to support life. The quest to find Earth-like planets is driven by our innate curiosity and the fundamental question, are we alone in the universe? These characteristics increase the likelihood that a planet could harbor life, at least as we understand it. Life as we know it requires certain conditions to thrive, and finding planets with these conditions is like finding a needle in a cosmic haystack. Scientists use advanced technology and methods to identify these potential Earth-like planets, analyzing data from telescopes and space missions. But what exactly makes a planet Earth-like? It's a combination of several factors that together create an environment where life could potentially exist. These factors include the planet's size, mass, composition, distance from its star, and the presence of an atmosphere. Each of these elements plays a crucial role in determining whether a planet can support life. First and foremost, an Earth-like planet should be rocky, like Earth, Mars, and Venus in our own solar system. Rocky planets have a solid surface, which is essential for the development of complex life forms. Unlike gas giants, which lack a solid surface, rocky planets provide a stable environment where life can potentially take root and evolve. This means its surface is composed of solid materials, unlike gas giants like Jupiter and Saturn, which are mostly made of gas and liquid. The solid surface of a rocky planet allows for the presence of landmasses, oceans, and other features that are crucial for sustaining life. The composition of the planet's surface can also affect its ability to retain an atmosphere, which is vital for protecting life from harmful space radiation. Size and mass are also important. An Earth-like planet should have a similar mass and diameter to Earth, ensuring its gravity can hold on to an atmosphere. The atmosphere acts as a shield, protecting the planet from meteoroids and cosmic radiation, and it also plays a key role in regulating the planet's temperature. A planet with too little mass might not have enough gravity to maintain an atmosphere, while a planet with too much mass could have a crushing gravitational force. Finally, and perhaps most crucially, an Earth-like planet needs to orbit within its star's habitable zone. This is often referred to as the Goldilocks zone, where conditions are just right for liquid water to exist. The distance from the star determines the planet's surface temperature, which in turn affects the possibility of liquid water. Too close to the star, and the planet would be too hot. Too far, and it would be too cold. This is the region around a star where temperatures are just right. Not too hot, not too cold, for liquid water to exist on the planet's surface. Liquid water is a key ingredient for life as we know it, and its presence greatly increases the chances of finding life. Scientists are particularly interested in planets within the habitable zone because they offer the best potential for discovering extraterrestrial life. Liquid water is essential for life as we know it, making the habitable zone a prime target in the search for Earth-like planets. The discovery of such planets not only fuels our imagination but also provides valuable insights into the conditions necessary for life. As we continue to explore the cosmos, the search for Earth-like planets remains one of the most exciting and profound endeavors in the field of astronomy. Finding planets orbiting other stars called exoplanets is no easy feat. These planets are located light years away from us, making them incredibly difficult to detect with even the most advanced telescopes. The challenge lies in the fact that these exoplanets do not emit their own light. Instead, they reflect the light of their host stars, which are often millions of times brighter. This makes spotting an exoplanet akin to finding a needle in a cosmic haystack. These distant worlds are incredibly faint compared to their host stars, like trying to spot a firefly next to a blazing spotlight. Imagine standing in a brightly lit stadium and trying to see a tiny firefly buzzing around one of the floodlights. The overwhelming brightness of the floodlight makes the firefly almost invisible. Similarly, the intense light from a star can easily overshadow the faint glow of an orbiting planet. To overcome this challenge, scientists have developed ingenious methods for detecting exoplanets, and two space missions, Kepler and TESS, have revolutionized the field. These missions employ sophisticated techniques and cutting-edge technology to peer into the depths of space and uncover these hidden worlds. The data collected by these missions have provided invaluable insights into the diversity and nature of planetary systems beyond our own. Launched in 2009, the Kepler Space Telescope was a pioneering mission dedicated to hunting for exoplanets. It was the first mission of its kind, designed specifically to survey a portion of our galaxy to discover Earth-sized planets in or near the habitable zone. The habitable zone is the region around a star where conditions might be right for liquid water to exist, a key ingredient for life as we know it. Kepler employed the transit method, observing a fixed patch of sky and looking for tiny dips in a star's brightness. This method involves continuously monitoring the brightness of thousands of stars and detecting periodic dimming events. These dimming events, or transits, occur when a planet passes in front of its star, temporarily blocking a small fraction of the star's light. These dips occur when a planet passes in front of its star, blocking a minuscule fraction of its light, like a moth briefly obscuring a distant street lamp. The amount of light blocked can tell us a lot about the planet, such as its size and orbit. By analyzing these light curves, scientists can infer the presence of planets and gather information about their characteristics. Building on Kepler's legacy, the Transiting Exoplanet Survey Satellite, or TESS, launched in 2018, continues the search for exoplanets. TESS is designed to survey nearly the entire sky, focusing on stars that are closer to Earth. This allows TESS to cover a much larger area than Kepler, increasing the chances of finding new exoplanets. TESS scans almost the entire sky, observing stars much closer to Earth than Kepler. By targeting these nearby stars, TESS can identify exoplanets that are easier to study with ground-based telescopes. This proximity allows for more detailed follow-up observations, which can reveal additional information about the planet's atmospheres, compositions, and potential habitability. This allows TESS to identify smaller planets and those orbiting brighter stars, making them easier for follow-up observations and characterization. The discoveries made by TESS are helping to expand our understanding of the universe and the variety of planetary systems that exist. Each new exoplanet found brings us one step closer to answering the age-old question: are we alone in the universe? While the transit method employed by Kepler and TESS has been incredibly successful, it's not the only way to find exoplanets. The transit method involves observing the slight dimming of a star as a planet passes in front of it, blocking a portion of the star's light. This method has allowed us to discover thousands of exoplanets, but it has its limitations. For instance, it only works if the planet's orbit is aligned in such a way that it passes directly between its star and our line of sight. This means that many exoplanets could be missed simply because their orbits don't align with our viewpoint. Another powerful technique is the radial velocity method, also known as the Doppler wobble method. This method has been instrumental in confirming the existence of many exoplanets initially detected by the transit method. It works by detecting the tiny wobbles in a star's motion caused by the gravitational pull of an orbiting planet. These wobbles cause shifts in the star's light spectrum, which can be measured with high precision. This method relies on the fact that a star and its planets orbit a common center of mass. As the planet orbits, it exerts a gravitational force on the star, causing it to move in a small orbit or wobble. This wobble is incredibly subtle, often only a few meters per second, but with advanced instruments, astronomers can detect these minute changes. As a planet orbits its star, it causes the star to wobble ever so slightly. This wobble can be detected by observing the star's light spectrum. When the star moves towards us, its light waves are compressed, shifting towards the blue end of the spectrum. Conversely, when the star moves away from us, its light waves are stretched, shifting towards the red end of the spectrum. Astronomers can detect this wobble by observing the star's light. They use spectrographs attached to telescopes to measure the star's light spectrum with great precision. By analyzing the shifts in the spectral lines, they can determine the star's motion and infer the presence of an orbiting planet. This method has been particularly successful in detecting large planets known as gas giants, which exert a stronger gravitational pull on their host stars. As the star moves towards us, its light is slightly compressed, shifting towards the bluer end of the spectrum. This phenomenon is known as the Doppler effect, and it is the same principle that causes the pitch of a siren to change as an ambulance passes by. The amount of shift in the star's light spectrum can tell us about the speed and direction of the star's motion. Conversely, as it moves away, its light stretches, shifting towards the redder end. By measuring these shifts over time, astronomers can create a detailed picture of the star's motion and the influence of any orbiting planets. This method has been used to discover many of the first exoplanets, including some of the closest to our solar system. By measuring these subtle shifts in the star's light, astronomers can infer the presence of an unseen planet. This method is particularly useful for finding planets that are too far away or too faint to be detected by other means. It has also been used to study the atmospheres of exoplanets by analyzing the light that passes through them during a transit. These two methods, the transit method and the radial velocity method, complement each other, providing different pieces of the puzzle in our quest to understand exoplanets. While the transit method can tell us about a planet's size and orbital period, the radial velocity method can reveal its mass. Together, these methods allow us to calculate the planet's density, which is crucial for understanding its composition and potential habitability. The transit method reveals a planet's size and orbital period, while the radial velocity method allows us to determine its mass. By combining these measurements, we can calculate the planet's density, which gives us important clues about its composition. For example, a planet with a high density is likely to be rocky, like Earth, while a planet with a low density is likely to be gaseous, like Jupiter. Combined, these measurements provide crucial information about the planet's density and composition, bringing us closer to identifying truly Earth-like worlds. By understanding the properties of these distant planets, we can learn more about the potential for life beyond our solar system. The search for exoplanets is not just about finding new worlds. It's about understanding our place in the universe and the potential for life elsewhere.